All right, sorry for the delay, folks. I'm just getting things set up here. We'll get started in just a second. Apologies for the delay. My machine appears to be having quite a lag issue. I'm trying to just scroll and it's happening like a second afterwards, but I feel like it'll stabilize shortly, so hopefully we'll get that going. Okay. Cool. So do a little sanity check here, make sure my environment is okay, and we should be off to the races. Okay, cool. It's working. All right. So, as usual, uh, welcome to Study Hall. This is a venue for you to come by and ask questions. It looks like somebody put a question in Slack. So, thanks to the person who did that, and I'll be going through their question. They've got a little. They put a link in, and then they're just asking the question. Hi, Clark. A couple of classmates and I are working at the current problem of list accumulators number 3. We're having an issue in understanding how to go about taking an input as a list and returning a list of each element's divisor as the solution. Okay. I think that'll be more clear. I think this was number 3. We're saying in list accumulators. Okay. Oh, this is number 4. So finish writing the function divisors according to its docstring. So I'm just going to paste this in to here and work out of my replit. And I'm just going to copy in the person's question so I can make sure that I address the questions that they have. Okay. Number 3. So the issue, having an issue understanding how to go about taking an input as a list. So let's see. Let me try to find, input. Okay. So I'm not sure if there's potentially, not sure where you and your classmates are at, but the way this is stated makes me think of like the input function. I've done this question recently, I think, and either in a mentor session with somebody or perhaps a recent study hall. But most of the, I mean, I can tell by looking at this, and most of the questions in Learn don't take an input using the input function. When we use the word input, it kind of gets thrown around to mean a few different things sometimes. So we have, let's let's chase that out and just kind of look at what that means. We have the input function. This is a function called input. It prompts the user with whatever string you pass it. So input your name. So I could say name equals this, and so it prompts the user with whatever you ask it to prompt with. Should put a colon and a space there. And then it returns a string, which is whatever the user inputted into the terminal. And then we can say hello name, right? So if I run this, and this has right now this has nothing to do with the function here, but I'm just trying to, and apologies if I'm misunderstanding your question, but it might be me just missing the obvious, but the way it was stated makes me think that, you know, I want to clarify the input function versus like arguments and other things. So yeah, so this is how we could use the input function. So input your name. I could say my name is Fred. How about that? Oh, parent again. Print. There we go. Okay. Let this run again. Fred. Hello, Fred. Right. So we can capture that in a string, or we can capture that string that input returns in a variable and then utilize it wherever we want in our code. Right, so that's one thing that input means. Another thing that input means is something kind of completely different. So sometimes we'll talk about the parameters of a function being an input, and similar to this, the arguments of a function being an input. Okay, and then we have an addendum to that. Looks like I did misunderstand. Let me get to that in a second. So they're saying, sorry, what I meant was taking in the current input of in, which is a list. Interesting. Parameters. So the input, it looks like here the input is just meant to be an integer. And then the output of this function is a list. So apologies, I may still be misunderstanding. So in itself is a list of 4 items. So this is supposed to, in itself is a list of 4 items. 3 of which are inputs. The confusion is how to guarantee a list of divisors for each input. Yeah, so what I'm seeing is that in is just a single integer. But let's just go through this problem and maybe I apologize because sometimes I just miss really obvious things and I just need to like recontextualize it. But yeah, I'll just go through a solution for this, and we will go from there. So I'm going to test this in a for loop. I'll say for I in range, what did I do? 20. We'll do 1 to 20. So returns a list of proper divisors of n. So a proper divisor is going to be a divisor, a number that divides evenly into n, but not n itself. So it will not include n. So let's do this. Let's say I'll initialize my list equals an empty list, and I'll return it because I know that's what I'm going to return. And then from here we can do for I in range 1 to 1 to n, if n mod I equals 0, list dot append list dot append I. Cool. So this should check every number starting at 1 all the way up to n. Obviously 1 is a divisor of everything, so that'll just get added in. This is not the most efficient, but this will work. This will just work. And we'll do this for all the numbers between 1 and 20. Oh, I see. Okay. So yeah, it looks like the person who's asking this question is saying that yeah, they missed that the portal is running 4 different tests. Those tests might be in a list. I don't know those tests off the top of my head, but it wouldn't surprise me if they're in somewhat of a list, and then those are different values of n and being used to test against. And then somebody also asked, can I explain what a proper divisor is? I think there might be there's a bit of a delay, but I will explain this again just to be clear. So all that's meant by a proper divisor is a divisor of n that is not n itself, right? So we could argue that 1 and 2 and 5 and 10 are divisors of 10. But a proper divisor is just 1, 2, and 5. So the proper divisors of 10 are all the numbers that divide evenly into 10 except for 10 itself. It always, there's sort of an asymmetry that creates, like where you include 1 but you don't include the number itself, and that always bothers me. So I always end up writing divisors either to exclude both 1 and the number itself, or to include both of them. But yeah, that I didn't define the term proper divisors, and I didn't invent math, so I don't get my way on this one. But a proper divisor, despite what I want it to be, is all the numbers that divide evenly into a number except the number itself, right? Let me know if that helps answer your question. Cool. This is funny because I've come across this question in various forms. It pops up a couple times in our material under different names. I usually call this factors list, but this is actually a function that you'll write fairly often to get a list of divisors or list of factors of a number. If I were writing this myself, I'd probably call it a divisors list or a factors list or something like that. But I want to show an interesting. Just earlier today, I went over this with somebody, and yeah, there's sort of some interesting optimizations that you can do. So this does work in its current form. That's fine. And let me see if I can just grab this code really quick. Let's see if it's still here. Da-da-da. So I encountered a problem on Code Wars, which I will try to remember to. It's an interesting problem, a rather hard one too. So if you're a beginner and if you're having trouble with it, no worries. It's legitimately challenging problem. But it required that we get the sum of divisors. So I wrote just a regular divisors function like this, and we kept getting a timeout, so we needed to optimize it. So while we're here, since I've literally gone over this question and optimizing it like 3 or 4 times in the last 3 or 4 days that I've worked, which is kind of interesting. We'll just use this as an opportunity to talk about optimization, because it's a topic that I tend to encourage people in the context of premium prep and prep in general. I tend to encourage people to like not worry about optimization. And the truth of the matter is, like, a lot of times what matters in your code is that your code works. So I tend to teach in a way and like guide people towards a way of coding that's like maybe kind of brute force, but it's simple and it works, you know. So sometimes, you know, the kind of solutions that I push towards are maybe inelegant, maybe they're a little ham-fisted, but they're simple and they just work. So that's a very easy way of coding, but I do really like optimization. I like the challenge of taking a working solution and optimizing it. So just for fun, let's do that. Let's do that here. Also, if anybody has any other questions, feel free to pop those in. Cool. So let's call this, this is just the code from above. I'm just going to call this factors list, because I don't know, that's the name I prefer. So this is the simple code. And then this is the optimized code. I'll just write this out. Def factors list. I'll take in. And I'll do this with a list. At first, we're going to end up with this being a set. But I'll do it with a list, and I'll show you why we use a set in the end. So I'll say list equals empty list. And so the big place where we can gain a huge optimization is in the range, right? If you think about this range, we're checking a lot of numbers that we don't need to check. The simplest kind of obvious optimization is to iterate up to half of n plus 1. So we want to include half of n as well, right? Because half of 10 is 5, and 5 is a valid divisor of 10. So we want to check 5. We want to check 5 as well. So what we can so what excuse me. So what we can do here is this is half of n plus 1, which includes it, and then we're casting it as an integer because we can't use a float as a range. I could do double slash division, but it's just my habit to just cast it as an integer like this. It's eccentricity of my own code. So cool. So let's see, for I in range, we want to start at, I'm going to start at 1, and I'm going to go up to int. So what we can actually do, we can reduce the size of numbers down even further. And this this will tend to kind of like give us more and more relative benefit the larger the number gets. I think the efficiency relative to checking half of n or all of n, I think increases exponentially with a larger and larger number. And we'll test this with a really big number and see how much faster it is. It's pretty cool. Okay, so we can reduce it down from half even further to n to the power of 1/2, 1/2, which is, and we'll include this as well, +1. And I can do the +1 inside or outside of the int. I'm doing it outside up here and inside up in here, but 6 of one, half a dozen of the other. So this is actually the smallest set of numbers that we need to check. So if we have a test, and I'm breaking my own rule, I should have had a test in place for this before we even started, but factors list 10, factors list 10, there we go. So we'll just imagine 10, right? So the square root of 10 is 3 point something. I'm not really sure what it is. But if we cast the square root of 10 as an integer and add 1 to it, we get 4. Range goes up to, but not including that number. So really, we're just checking including 3. So since we're starting at 1, the numbers that we need to check for 10 are 1, 2, and 3. So we only need to check 3 numbers to find all of the divisors of 10. And we could do this with proper divisors or whatever, inclusive divisors. I don't know what the other one's called. Regular divisors or something else. So still have to do the same thing. If in mod I equals 0, if in mod I equals 0 tells us if it's a divisor, is I a divisor of n. If it is, we will list dot append. Now here's where things get tricky, right? So we know that 5 is a divisor of 10, right? So let's write our expectation here. We want to include 1, 2, 5, and I'm just going to include 10. Excuse me. Yeah, so we know that we have to include 5 and 10, but we're not even checking 5 and 10, right? We don't need to check 10. We can assume 1 and the number is are factors of itself, right? But we want to include 5, and we're not checking it. So here's the thing. Factors other than squares tend to come in pairs. Well, factors other than squares do come in pairs, always come in pairs, right? So 2 is a factor of 10 because it goes into 10 5 times. So therefore, 10 over 2 is 5. So if we say n over I, that's going to give us 5, right? For 1, this is going to give us 10. And then we also want to add in I if it's not. So I is also a divisor, right? If n over I is a divisor, then I is also a divisor. So we also want to list.append I if I is not the same as n over I. The scenario where that can occur is with squares. So 4 goes into 16 4 times. So 4 times 4 is 16. 4 squared is 16, right? So that's the scenario where we want to make sure we only add it in once. This will add it in once. So if we say if I not in list, so if it's not already in there, append I as well. Cool. And then after we're done, we will return list. This will just take forever and a half to run. Okay, there we go. Oops. Let me cast that as an int. Okay. So 10, 1, 5, and 2, right? So one slight disadvantage of this approach is that the numbers are not sorted, right? So we could sort, although we could just return the sorted list, although this does add some computational overhead. So in order to get around this, now that we live in the era of sorted sets, we already can determine that we're not adding in duplicates. So I'm going to call this set underscore equals set, a new set. And instead of append, we use add. And that'll enhance it as well. Cool. So let's benchmark these really quick. So let's do something like 100,000 million. We'll do 100 million. So we'll check for the factors of 100 million. So we'll see how fast. So this is the optimized one, the first one. We'll see that result first, and then we'll see the other result later. Oop, and then actually let me cast my output as a list again, which is a pretty low overhead operation. Okay, cool. So that's running. I'll let that cook. All right, first one's done. Waiting on the second one. Still going. I can hear my fan in my computer picking up. Okay, there we go. Looks like it's done. Yep. Cool. All right. I'm just looking at this, and this actually does not look like it's sorted, so that's kind of interesting. Huh, so maybe for very large sets. So yeah, so that's the thing. This actually shows you never rely on the order of a set. Because as soon as you count on it being sorted, it's not going to be sorted. But these do appear to have the same values, so I'm going to let it slide. Cool. Anyways, thought that'd be fun. I know a lot of people are like excited about writing super optimized code. I'm definitely not against it. I do shy away from it. I do kind of encourage people away from it a little bit because you don't have to be able to do this to be able to like program and get things done in Python. You know, like if you can do this, you know, and I would say like if you can do this and optimize it with like going through half the range uh, in over 2, you know, like that's a great optimization. That's going to make this function work well twice as fast. So that's a huge improvement, and it's a really small lift to make that optimization. Whereas this is a huge improvement, or like, well, the other one is a huge improvement. This is even way huger. I'm guessing here, but I'm guessing this is possibly 100 or more times faster than the other way. So, and that's because we check so much smaller of a range. Cool. All right. Let's see here. And I just wonder if I can get this solution to pass the tests in Learn. Let me see if I can. And then I got to make it proper divisors, so I have to exclude. I have to exclude the number itself, so I'm just going to start here and include 1 in the beginning. We'll do that. Was this a syntax error? I think that might have been a syntax error. Okay, that does work. Extreme optimization. Cool. Lots of fun. Okay, looks like we got another one. Says, hi Clark, I don't have a link for this problem. That's okay, but posted it in. Okay. This is the for loop version. Why does it work for negative numbers and 0? I'm having trouble understanding the logic. Get divisors. Or why does it work for negative numbers? Hey, yeah, you're welcome. Let's see. Oh, why doesn't it work for negative numbers? Let's see here. So the reason it's not going to work for negative numbers is because, so sorry, the wording in your question was why does it work, I believe. But there's a does and a doesn't about the working of this, so excuse me. The reason it works in that it's valid code that doesn't throw an error. Let's address that, and then we'll address why it doesn't give divisors for negative 90. So the reason it works is that, so imagine negative 90 is going to create our range here. So 1 to n plus 1 to number plus 1. So that's range 1 to negative 90 inclusive. This is what we call an inverted range, because if I try to, I'll comment this out. Let's see, make sure. Okay, we're good. For I in range 1 to negative 10, I'm not passing in a step here, a step parameter for range. Therefore, it assumes the step is negative 1, right? So we can assume, or excuse me, it assumes the step is positive 1. We can assume a step of positive 1, which means we're counting from the right, or from the left to the right. We start at 1 and we go in steps of positive 1 up to the upper bound. But this is inverted because the upper bound is less than or equal, in this case less than, the lower bound. So how do we take steps from left to right starting at a number that is to the right of the number we're supposed to end at? if I print I, and then I'll print fin. Go away, go away. So all we get is fin, right? So our program ends without ever executing any of this code. So in order to have a range from 1 to -10, we have to take steps of -1, right? So the reason this doesn't work with, the reason this is valid is that it's valid to write a for loop with an inverted range. An inverted range doesn't do anything, but it works. It's valid code. Python will say, I can't do anything. I'll move on. This is the kind of thing that you might think would throw an error, but it doesn't, and that's actually useful in a number of cases, right? So in this case, we start at 1, 0, -1, -2, -3, all the way up to -9. So yeah, that's an example of that. If we wanted this to work with negative numbers, we would have to do something. There's probably some really cool kind of crafty way of doing this. I mean, the question is though, do we divide? What is? Huh. Actually, let me try this out here, right? Let's just try this out. So, for I in range 1 to -10 and steps of -1. Let's do this. N equals -10. So we'll do n there, and we'll say print I, n over I. Oops. If I not equal to 0, print n over I. Yeah. And let's start at -1. Actually, that will save us from needing that line, that condition there. So, oops. If I say n, I'll do an f string here. So I say n over I is n over I. N over I is n over I. We'll just say equals. Okay. So it looks to me -10 over -1. So if these were positive numbers, 10 over 1 would go in evenly. But I guess I could do, sorry, I guess I could do mod. It's mod that I'm interested in, actually, not regular division. That's why I'm not getting the result that I thought I would. Confused myself. Okay, so yes. So there are scenarios where this will give us 0. And it's at, we do plus 1, we have to do -1. Ah, okay. Cool. Yeah, so these are at the same numbers here, right? So it occurs to me that what we could do is, if we wanted this to work for negative numbers, we could do something like I think there's a nice easy way of doing this. Yeah, I just need to do a condition. I'm trying to avoid writing a condition, but I just need to do that. So if n is less than 0, then it's negative. We can do sign equals -1, else sign equals 1. So as we append, we can append multiplied by sign, and then we can normalize this number by getting the absolute value. We can do to the power of 2 to the power of 1/2. So this will give us the absolute value. So this is the square root of the square. So if you square a negative number, -4 squared is 16. The square root of 16 is 4. So this effectively just normalizes, or it gives you the absolute value. Okay, so that gives us the absolute value of that. So now we can just do range 1 to the absolute value of the number, which is the positive expression, the positive value of the number. So it's distance from 0. It's positive distance from 0. And then we can multiply it by sign. If n was less than 0, sign is going to be -1. Which means we'll multiply the divisor by -1. And if sign is not less than 0, we'll multiply it by 1, which is just going to be divisor. So multiplying it by -1 will just make it negative. So let's just, let me actually activate these tests. We'll go from there. Also, let me know if this is helpful. N is not defined because it's not called n, it's called number. Where is it? Number. Yep, there we go. So used to calling it n. Float cannot be interpreted as an integer. Well, you don't say, do you? Int. Another advantage of constantly using parentheses is if you need to throw something in a function, well, you already have the parentheses. Okay, cool. So obviously 0 has no divisors, but yeah, this looks like 1, 2, 3, 5, 6, 9, da, da, da. Cool. Yeah, let me know if that's helpful. Oh, looks like, so they're saying, I thought an edge case would be needed, but no edge case was necessary. Returns an empty list. Yep, cool. Yeah, a lot of the questions in Learn, like you can just think about like, what's the problem, I think, are generally pretty well written. Sometimes our we make our best approximation, and then when we realize, oh, we could make this clearer, we'll go back and kind of try to fix things up like that. But In general, I think our copy is pretty good, and we sort of follow a rule of if there's like the if there's an edge case, we will generally state it explicitly. Sometimes that will be kind of up to you, but also if it's up to you, it'll be kind of clear in other ways. So yeah, generally you can just kind of solve for what's being asked. And you can always be like, well, I'm not sure about, if you think, oh, there might be an edge case, just try to solve it without the edge case. And if it fails on a test that shows you that that edge case is there, then you have to take it. But yeah, anyways, good question though. Very good question. Cool. All right. I'm not seeing any other questions. Kind of want to just give people a minute, just to see if we get another couple questions in here, because I think that's really the, like that's the drive behind study hall. That's what makes it good. So if you've got a question, if you got something you're working on, I'll give you all a minute to get something and pop it in. And it can just be something, maybe you solved something and don't know how it works, or that happens occasionally, or you solved something and you want to know why it works a certain way. Like this last question was good, because it's like, well, I got it working, but why isn't it working in this particular way? I'm happy to take questions like that. So uh, if it's from Learn, it's helpful to have a link, and if not, then that's fine too. But the stuff in Learn, it's nice to have a link so I can just go to it and prove that it works. Somebody's asking you to see the solution to the challenge again. The challenge on divisors. Yeah, let me actually just put in this code really quick. So this is a solution that, or let me just do this. I'll say handles negative numbers. We'll say highly optimized solution. And then this is really just the regular solution. Let's call it a simple solution. Simple and slightly optimized. Let's just slight, but I call it slight, but it's slight because it's easy. Easy but significant optimization. Let me do this for you. I haven't tested the solution that does negative numbers. Actually, I just realized it won't work because we're including in here. And this explicitly asks us to exclude n, which is kind of weird, but it does. Let me just handle this deeply nested parentheses. Okay, actually did use too many parentheses. There was actually genuinely an extra set in there, but that's the thing. If you use too many parentheses, as long as they're matched, like, it's still gonna work. Okay, and then let me actually put this in. Oh no. Slack. Oh. Oh my gosh. Okay. I hit the wrong shortcut key in Slack and it freaked out. So there's 3 solutions to the person asking about that. It looks like we got another question in, which is great. Comment these out and we'll go on to that one. Okay. There's not much description here, just a link to the problem. So I'm going to assume that you just want me to solve it and explain it. So if you have other questions about this, this is for the challenge number 3 in split and remove vowels. Mm. Okay. Okay, so write a function called split and remove. Split remove. This function should take a parameter called the string, which is a string. I don't know. Contains a string. This function should return a list of the given string with all the vowels removed. Be careful not to change the case of the string. Okay. Also, okay, all right. Also, for the purpose of this function, y is not considered a vowel. Is not considered vowel. Okay, so our vowels are A, E, I, O, U. Def split remove called the string. I don't know, does it really? I don't want to call it the stir. I don't like that name. I'm going to call it text. TXT. And then I want to do I want to accumulate? Yeah, I can think of a couple of solutions for this. So let's do this. Print split remove, and I'm just going to use, I'll just use the function name itself, split and remove, as the input. So it should return a list. Function should return a list of the given string with all I don't know if it. I don't know what it wants in the elements though. If it wants the substrings as delimited by all the vowels or the characters, so that's not entirely clear. I might have to go through and edit the copy on this a little bit. Okay, so split remove takes in text. Our vowels are A, E, I, O, U, and let's just do. I'm going to call this text in, and we'll call this text. I'll just call it text equals an empty string, and I could say for C in text in if C not in, and let's just do C dot lower. If C dot lower not in, I don't even need a variable, A, E, I, O, U. Just get rid of that variable. Text plus equals C. Return text. Okay. Oh, this is, we wanted a list, right? There we go. Spult RMV. Okay. So since I'm not sure what they want as the elements of the list, I have no expectation that it's going to accept this function. It's not entirely clear to me. Okay, that is what they wanted, evidently. Okay. So that works. So I was going to show a different way of doing this with split and replace. But it would give me the elements in the list would be delimited by the vowels, which is interesting, but it's not evidently what this question is asking for. I think that'd be interesting to do. So let's write a variation of this. So let's do it where the expected return will be a list where each element is created by delimiting or is delimited by the vowel. So like this. Cool, and we'll remove the vowels here. So this will be interesting. Cool, you're welcome. If anybody else has another question, feel free to pop it in. But I just sometimes I do this thing where I'm like, oh, it could. I'm not sure if it's the one way or the other way. You know, if some question is a little bit ambiguous. Like I said, we try to make our questions not ambiguous, but you know, it's it's a challenge sometimes, and that's fine. You know, just a little copy editing as we go is what we do. So yeah, so sometimes I'm not sure if it's one way or another way. So I'll solve for one way, see if it's that way, and then if it's not, I'll solve for the other way. But sometimes I'm like, I wanted to do the other way, so we'll do the other way as well. So okay. So what we can do is yeah, we'll just accumulate right onto our input here. And I'll A, E, I, O, U. And I think I got to do a IOU as well. We can say text equals text dot replace. Here's a trick. So I'm going to replace every V with some other vowel. It literally doesn't matter which one. Just a single vowel, and I'll use a lowercase a. And then I'll return text dot split lowercase a. Cool. Looks like we've got an empty string at the end, which is rather interesting. But I don't know. I don't care that much. That's fine. So that's basically what I was expecting. So that's kind of fun too. Sort of the cool thing about this is we can we can replace if we have multiple things to split on. And somebody who's in study hall asked about this in premium prep yesterday. If we have multiple things we want to split on, we can go through and replace all those things, everything that we want to split on. So if I wanted to split on, let's say I wanted to split on periods and question marks and exclamation marks, right? So these are different kinds of delimiters for different kinds of sentences, right? A sentence or a sentence that ends in a period is a statement, or an exclamation mark, I think, is a loud statement, and then a question mark is a question, obviously. So, but these are delimiters for different kinds of sentences. So if I wanted to split some text across multiple sentence delimiter characters, I could replace all of them with one of them, right? So I'll replace all the dots with dots. I'll replace all the question marks with exclamation points. Or if I'm replacing all the dots with dots, I don't really need to replace the dots, right? I can just do this and this and turn them into dots, and then I can split on dots or on period. And then that'll split a body of text into its constituent statements and questions and loud statements. So yeah, that's just something cool you can do for split. I'm just wondering how to do this. Okay, now I'm wondering how to do this in a comprehension. I'm like, I should be able to do this in a single line. Okay. This is quickly, I think I can just do dot join, and we'll do like this. That's not gonna work. Yeah, because this isn't really a regular accumulator. Okay, I have to think on that one to see how I can do that in a line, but I bet it can be done. I bet it can be done. Okay, cool. Lots of fun. Lots of great questions today. Thank you all for bringing in your questions. I love it. That's what makes study halls fun. I think for me, and I think for other people, just taking questions and seeing where people are at. So I'll give people another. I'll give people a minute or two here to bring in a question, and if I don't see anything, then I'll start going through the material if I don't see anything. But yeah. And if you've already asked a question, feel free to ask another one. It's slow right now, so yeah, you wouldn't be hogging the space or taking up too much space. It'd be fine. Cool. I'm not seeing any other questions. That's okay. So I think we'll just go into covering some of the material. Do feel free to pop a question in though. If I haven't made that abundantly clear, I feel like a broken record, but if you don't have a question, that's fine too. So we talked about this recently in Premium Prep. We're at about the same place in Premium Prep as we are in the study hall streams in terms of going through the material. We recently talked about breaking loops. I think did I do these? Yeah. So loops have a couple of additional keywords that allow us to control them with more precision. So let's see here. Trying to think of like a good example for break. There's the I'll just do the is prime function. So if we do def is prime, take in, oops, and we'll do the Boolean flag way. Prime equals true if n is less than 2. Prime equals false. For I in range for I in range. Let's do, oh yeah, in, sorry, 2 to n, for I in range 2 to n. Yeah, we'll just do over 2, make that an int. Okay, we'll include that as well, +1. If n mod I equals 0, then prime equals false. And then return prime. Right, so we have 2 points at which prime can be set to false. In this case, if we're doing the number, if we're seeing if 10 is prime 10, this will work correctly. Wow. So much lag. Okay, so this will work correctly. This should work correctly. We know 10 is not a prime number. So let's print out all the numbers it's checked. Print F checking I, right? And then if it's determined not to be a prime, n is not prime. Okay, let's do that. So I'm just putting these sort of debugging statements in here, right? So we're going to check every number from 2 up to half of n, right? Oops. So it starts with checking 2, and then it says 10 is not prime. Weird. Oh yeah, checking 2, 10 is determined to be not prime, and then we check prime to false. Then we keep going, and we keep checking 3, 4, 5, and then again 5. We check 5, and we determine that n is not prime. Again. There we go. And then finally we return false. So as soon as we determine 10 is not prime, we don't need to check any more numbers. We can break. So we'll run a break in there. So checking 2, 10 is not prime, and then false. So yeah, so that's how we can use break to kind of control our loops better. One thing here, if let's say I run this break in my code up here, then you can see it breaks the loop and it stops executing code. So it's not going to finish everything in that condition. It's going to just break immediately. So we can end up hiding code under break like you can under return. Hiding just means like it's probably a better word than hiding, but like hiding in this case just means you've hidden it so that it'll never actually run. Python won't throw an error or anything. This is valid code, but it's just there's no point in having these lines if they're going to be behind this break because they'll just never get run. And this actually gives us the wrong result since I broke the loop before changing prime to false, then it returns true for 10. So it's not what we want to have happen. So you got to make sure your break is in the proper place. The proper place being at the end of whatever branch of code that it's in. Cool. And it looks like we do have another question, which is great. Open-ended problems. All right, while loops. Oops, come on. Come on. So open-ended problems. We're at while loops, and this is challenge number 1, wondrous tests, or the wondrous test. Okay. I recently helped somebody with this one, and I've already forgotten it. I just recognized the name. I have no recollection of what this problem is asking. So this will be fun. So if n is odd, triple the number and add 1. I do remember this now. If n is even, take half of it. Repeat the process. This process, repeat this process. Okay, repeat this process until the number 1 is reached. return a list of all numbers that were iterated through. Okay. Parameters in, which is an integer, it returns a list. So let's say while, and I'm going to do what I prefer to do, which is while true. So this just loops forever, and I'll tell it when to stop. While true, if n is odd, let's see, if n mod 2 equals 1, n is odd. Else, fine, I'll put a pass in there. Else n is even. So if n is odd, we want to say n equals n times 3. Otherwise, n equals n over 2. And then we'll say if, oh, yeah, then we'll list dot append this. We'll list dot append n. We need a list equals empty list. And where do we want to put this? So I have to have my exit condition. I'm going to use n as the controller. So if n equals 1, return list. I think I want to do this last. I think that's it, right? So in this case, I mean, we were just talking about break. I could break and then return out here, but since I'm returning literally immediately after the break, I can just use return as my break, and that's what I prefer to do. Oh, well, probably got to test it. So I'm going to test it with over a range of numbers. I'll say for I in range. I don't want to do a big range. Let's do 1 to 100. Let's do 300. Okay. We'll print I and wondrous test of I. I'm worried I got into an infinite loop somehow. Oh gosh. What is wrong with me today? Ran my code, but didn't even have an invocation. Okay, let's do this again. Let's try this one more time. Yeah, we got an infinite loop situation. So I messed up somewhere. Pretty interesting result here. So let's see. If n is odd, triplet and add 1. Triplet and add 1. See, I totally didn't do that. Triplet and add 1. So when in doubt, read the problem statement. Make sure you did what it said it to do. Okay, there we go. Let's try that. That works. Hooray! Is it possible to not use while true? It's always possible to not use while true. It's hard. I get a lot of people who are like, oh, okay, so this is your way of doing things. This is my way of doing things because I promise you it's easier to just write a while true and then just tell it when you want to stop. But it's a fair enough question. Um, it's good to know how to control a while loop either way. So let's write it with while true. But first, let's look at all this insane. Oh my gosh, there's so many numbers. I did way too big a range here. Let's just try 100. There's something interesting about this output that I wanted to go over. Okay. And like this. Okay, cool. Let's just submit this and make sure it works, and then I'll look at the other way of doing this. So yeah, like I said, it is always possible to write a while loop without the while true. It's just usually easier to do while true and then exit when you're ready. Nope, didn't work. Doesn't like it. Oh, interesting. Very interesting. So somewhere I still went wrong. If n is even, take half of it. Repeat this process. Return a list of all the numbers that were iterated through. Hmm. So it looks like it wants this append. It wants it to include n. That's one thing, and it does actually expect floats. Which is kind of odd, but okay. Okay, so that works. Uh-oh. So what was the input for this? Oh, interesting. So I think I also want to test my exit condition right up front, right here. Yeah, let's do that. And this is what I actually prefer to do, is to have that exit condition up front. So make it easier to show when I convert it to a controlling it in the loop head as well. Okay, cool. Took me a couple attempts there, but so let's look at this with without doing a while true. So when you write a while true, you're saying, I will tell you when I found what I'm looking for. N equals 1, stop looping, means stop looping. You have to think in a negative with when you're doing it this way. So you have to kind of invert the way you're thinking, and then we'll take our return out here, and so while n equals 1, we can't do this. We could do while n while not n equals 1, or while n not equal 1, something like that. we could do this. And I think this will work as well. So it's kind of weird when you control the loop in the loop head. It's the condition. The condition, it should be true when you haven't found what you're looking for yet. So it's your continue looping condition rather than your stop looping condition. I find it much easier to think about like when to stop. The other reason why I think while true is better, a lot of times you'll sit there and you'll have a way of solving the problem formulating in your mind, but you'll be like, okay, well, what's my condition? And if you get it wrong, then it's you're going to get into an infinite loop. So you want to make sure you get it right. You have to think about it. So you have to like. Sometimes it can be really distracting. Is my point. So just out of pure laziness, I will just say like, you know what? I'll know it when I know what I'm looking for. So I'll just say like if found what looking for, break, stop looping. Just there's no reason to keep looping, and that just goes with a while true. So yeah, I encourage, if you're new to while loops, I encourage you to, if you find yourself getting stuck on that condition, just write a while true, and you're going to end up with something that actually is not only easier to think about, but gives you more control over the loop. Because you can put that exit condition in the beginning or in the end, wherever you want. So, yeah. And I guess to be clear, I'm not saying that you shouldn't try to understand it this way. Just don't get stuck on it, is all I mean. Cool. And then looks like we've got one more question here. We're at our normal stopping time, so I'll go through this question and we'll call it there. However, this one, we'll chase this out to the end. So if there are follow-up questions to this or whatever, that's fine too. Somebody's asking, is this a valid while condition in the example? This works, but it is not the same as yours, meaning mine. Okay, so let's look at this. If n greater than 0, yep, that's valid. This looks, I would say, I mean, this is not to the letter the same, but it's logically the same, right? So if we have list equals n, list density equals n while n greater than that's the same, n equals 1, n equals 1 break, yeah. So this condition is actually essentially checking for the same thing. I mean, I guess this is actually better because my code, if it ever got to be below 0, that could be. You still have your break condition for your while true, though. So you have two ways of controlling this loop. So you could, I don't know which one is going to be active. So you might, if you remove this, it might change the way it works. And you might have to change this to less than 1 or greater than 1. I think that might be the thing to do. But yeah. To answer your question, yes, this condition would work in some form. Cool. Seems like it's a kind of while true version. Yeah. All right. Cool. Well, I think that's that can be a wrap for today. Thanks for everybody who came in and brought in a question. I appreciate that. Yeah, that's what makes study halls fun and useful, I think. So I will see you all on Friday for next stream. I believe Tovio, I believe, is leading Premium Prep tonight. So if you're in Premium Prep, you'll see Tovio in there tonight. And then let's see, I'm just going to check the schedule real quick. Thursday. Wednesday is Tovio, and then Thursday I'll be teaching. So if you're in Premium Prep, I'll see you on Thursday. If not, then I'll see you on Friday. Y'all have a great rest of your day. Bye bye.